Hello everyone, welcome to the video lecture on query processing and optimization. In this lecture, we are going to discuss what are the different steps are involved when we execute a DML query and how we can optimize or how the DBMS optimize the query so that it produces the result in a faster manner. So in query processing, there are several activities are involved which are used for retrieving the data from the database. First, it will translate a query from high-level database language, in our case it is SQL, into a machine-level expression so that the machine can understand what the query is for. Then, on that machine-level expression, performs various query optimization transformation so that the query can produce result in a faster manner. Now, from the query optimizer produce a plan which is used to evaluate the query. Now, this in the next step, the query will act on the data and produce our final result. So that can be represented in this diagram. We write the query and our query will first go to the parser and the translator unit. Parser and the translator unit converts the query into a machine understandable relational algebra expression. Now, it not only generates one single relational algebra expression, but it generates several relational algebra expression. Not only that, it generates the several execution plan. So all those several execution plan will go to the optimizer, and optimizer will choose one of the execution plan depending on the cost. Cost means what? Cost means the time resources required for a query to produce the result. The execution plan which required less resource and less time will be chosen by the optimizer. Now to choose that one, optimizer uses a statistics about the data. There are several different ways how optimizer can work that will be discussed in this lecture. Now, when the optimizer generates a execution plan, that execution plan will go to the evaluation engine, and evaluation engine will work on the actual data and produce the output for our query. So query will go from parser and translator for error checking, and the parser translator will translate the relation into a relational algebra expression or different execution plan. All the execution plan will go to the optimizer. Optimizer will use the statistics about that data and select one of the execution plan. That execution plan which is most cost effective will go to the evaluation engine, and it will perform on the data to generate the output for the query. In this way, our DML query is processed. In query processing, the parser and the translator generates a parse tree to represent the query. In the parser step, it will check for any syntactical error in this query. Translator will generate the equivalent relational algebra queries for the particular query. Each query can solve in multiple ways. How it can, why we are saying so? Let us take this example. Here, show the name of the employee who are earning less than 4,500. So this can be done using several relational algebra query. In the first case, we are showing all the names. So we are showing those where the salary is less than 4,500. In the next case, we are selecting those employees where the salary is 4,000 less than 4,500. Then we are showing those names. So the same query can produce two different relational algebra expression. Now the relational algebra are not enough to produce or to tell you how to evaluate the query. we need to annotate it with the instructions specifying how to evaluate each operations. We will going to discuss about this. Now, a relational algebra operation annotated with instruction on how to evaluate it is called an evaluation primitive. Now, a sequence of primitives operation that can be used to evaluate a query is a query execution plan or the query evaluation plan. Different evaluation plan for a given query can give different costs. So the parser and translator actually gives you the query evaluation plan, multiple query evaluation plan. After the parser and translator generates that evaluation plan, it will go to the optimizer, and the query optimizer will choose the most cost effective execution plan, and that will go to the evaluation engine. Now, this is an example of our execution plan. In the first relational algebra, where we are projecting the name, then we are selecting those names where the salary is less than 4,500. So this is a evaluation plan for this relational algebra expression. Similarly, for the second relational algebra expression, where we are selecting the employees where the salary is less than 4,500 or projecting their names, this diagram can represent that one. Now suppose there is a index on the salary, right? So why do we need indexing? Indexing will help us to retrieve the data in a more faster way because it reduces the time for searching. So let us take there is a index, the name of the index is index 1 on the salary. Now using that index 1, we can retrieve those data where the salary is less than 4,500 more faster way than this one. So if there is an index, then in the annotation we must say that use the index 1. So this is the part, this is the annotation we have explained, we have discussed over here. So not only the relational algebra but the annotation how the algebra can perform. So this is an example of evaluation primitive. Similarly, this is a evaluation primitive, and in this case this is a evaluation primitive as well as this one. Now in this case this is a evaluation primitive and this is a evaluation primitive. Now sequence of evaluation primitive will give me the evaluation plan or execution plan. So these are the execution plan for the same problem, which is show the name of the employee who are earning less than 4,500. Now all this evaluation plan will go into the query optimizer, and query optimizer will choose one of them which have the lowest cost in the sense of time, in the sense of resources. Now the question is, why do we need query optimization? Because it provides the user with faster result, as well as it allows the system to service more query in the same amount of time, because as it requires less resource utilization, so in that time other query can also be performed. Now query optimization ultimately reduces the amount of load on the hardware, obviously, as it is required less amount of resources. So there are broadly two ways a query can be optimized. The first way, we analyze and the equivalent relation transform the equivalent relation expression. In this step, we try to minimize the tuple and the column count to be processed in the intermediate or the final query. So our focus will be on how we can give less number of tuple or less number of columns or attribute to the intermediate query or to the final query so that it reduce the working load of that regular expression. In the second way, we are going to mainly focus on this type of query optimization. This is called the cost-based query optimization. Now, in the second type of query optimization, it optimizes how the tuple are accessed from the data structure in where they are stored by using indexing, by using hashing, by using efficient data retrieval technique, and by using efficient data structures to store the indexing or the data like B tree or B plus plus tree. Now we are mainly concentrate on the how a relational algebra can be convert into its equivalent relational expression so that the cost can be reduced. There are total 12 rules of equivalent between the relational algebra expression. We are not going to discuss all the 12. So we are going to discuss 2 or 3 of them with examples. Now let us discuss the minimum equivalent expression. Two expressions on same relations are equivalent if for any instance of database meet at any point of time for any data if the relational algebra produce same result, then we are going to say that these two expressions are equivalent. In this case, we are producing the Cartesian product of relation E1 with relation E2, then selecting the tuples depending on the theta condition, which will be equivalent to the theta join between E1 and E2 relation. Similarly, this is called the theta join is commutative. So relation E1 theta join relation E2 is equivalent to relation E2 theta join relation E1. Similarly, a selection depending on the theta 1 and theta 2 condition on the relation E is equivalent to selecting the tuples depending on the theta 2 relation and selecting from the resultant tuples using the theta 1 condition. So these are 3 examples of equivalent expression. There are 12 relation equivalent expression in total. We are not going to discuss all these 12. We are going to mainly focus on these 3 to give you an idea. So a set of equivalence rules is said to be minimal if no rule can be derived from any combination of the others. We are going to see with an example. A query is said to be optimal when it is minimal. So let us take an example. Here we are considering 2 relations, employee and the department. Employee have the employee number, employee name represented by ename, job, his job profile, date of joining, salary, and department where he is working. Now department have department number, department name, and its location. Now my query is show the name of the employee and their respective department name. So this query I have solved in 3 different ways. Now in the first one we are going for the cross product and selection on this condition. This is my theta. In the second one we are going for the theta join approach. This is my theta. So as we know that as from this equivalence expression, we can say that these two are equivalent. Similarly, here the number 2 and number 3, you can see that I have just change the position of the relation. Department is in my left and the employee is on my right of the theta joining operation. So by commutative property of the in a theta join, we can say that these two are equivalent by using this rule. Now, which one will be the most cost effective? For that, let us assume that there are 10 data, there are 100 data, and here I have 8 data. So total 100 employees, and there are 8 different departments available. So in cross join, we know that all the rows of the left relation will be combined with all the rows of the right relation. So in our case, it will generate 800 rows, and from that 800 rows it will select those tuples where the condition is satisfied. Which condition? The department number of employee and the department number of the department will be same. So first it will produce 800 rows and then it will select some of them depending on the theta condition. Now this will take much more amount of time with respect to if we perform the theta join. Here, here we are performing the theta join between employee and the department. So it will join those rows where the theta condition is matched. Other rows will not be considered. So this will take less amount of time to produce the result. Now in the third case, though it is a theta joining, but as in the left hand side of the query there are less numbers of rows involved, then it will take less amount of time than the second query where we have performed employee theta join between employee and the department. So all those three queries will produce result, but the third one will produce result in more cost effective way. But this is not the optimal one. The reason is that you can see that depending on the query, depending on the problem statement, we need only the name of the employee and the department name. So instead of giving the total department table and the employee table in the joining, if we give the department number and the department name along with the employee name and his department number, then perform the joining, it will reduce my column count, which is one of the criteria to optimize our cost, right? So by this, in this way, we can even produce a more cost effective query. But we do not do that. Why? But we simply write in this manner. The reason is that we or the programmer need not to produce the optimal query by himself. The query optimizer will analyze the evolution plan or execution plan depending on the statistical data available and generate the evolution plan which will give me the optimal result. So if we convert all this query into its equivalent relational algebra expression, then those relational algebra expression will go into the query optimizer. Then it will select on the best one depending on the cost. That is how the query optimizer work. And as the query optimizer is there, so we need not to concern about how to write the optimal query by ourselves. Now let us come to the example number 2. Here the right hand side of the expression, here this expression will be much more cost effective than this expression. The reason is that Here we are reducing the numbers of tuple from the relation E by using the condition theta. Then the relation will go into this selection which have less amount of data to be function on. But in this case, in the first case, we are giving all the data of the relation E into the selection, so it will take time. Now, in this case, we are actually reducing the or minimizing the number of tuple in the query in the relational algebra expression. So let us take an example. Show the name of the employee who is a manager and earn more than 50,000. So the query we can write like this: select ename from employee where job is equals to manager. This is suppose my theta 1 and salary greater than 50,000. So this is my theta 2. This is my theta 1 and this is my theta 2. So what we are doing, as there is and, so we are actually perform selection theta 1 and theta 2 on the employee E, right? So we are evaluating this one. Now this type of this can be reduced by using this scheme. Here what we are doing, we are not giving all the data to the outer query. We are selecting those employee and their job where the salary is greater than 50,000. So what we are doing here, we are performing selection depending on theta 2. This is my theta 2, right? In the first case, we have considered as a theta 2, and this is my theta 1. Now we are selecting the data on the theta 2, then we are selecting the data depending on the theta 1. So as here in this case, the numbers of tuple will reduce depending on the salary or the theta 2. Then the outer query will need to work on less amount of data. As it need to work on less amount of data, so it can produce the data in less amount of time. Just now remember one thing, we will just write one of the query and the query optimizer will choose the optimal execution plan depending on the statistics performed on the data, and that plan will be executed. So we, the programmer, need not to worry about the how to write the optimal query. Now, as I have already told you, there are 12 equivalence expressions available, and the query optimizer will convert a query into its equivalence expression to reduce the cost of the query. Now I will recommend you to go for this, go to this link so that you will have a good idea about all the 12 equivalence expression and how they can reduce the cost of the query. So that's it for today's discussion. Thank you and see you in the next lecture.